Okay, so now we'll start with module 1, which is graph theory. Now, some of you may not be familiar with graphs, some may be already familiar. So, to bring everyone to be on the same page, I'll start with the very fundamental things about graphs and then we'll slowly build on the complexity. Okay, so a graph is a kind of data structure and it is modeled as a collection or set of nodes, which are also called vertices, and links, which are also called edges. So throughout this course, we'll use these terminologies interchangeably. So we're also going to model the network as a graph. So network means a graph in this course, as well as nodes, users, entities, whatever is modeled as it as is called a vertex from a graph point of view, and the interactions between these nodes is modeled as links or edges. They mean the same. Now, a graph could be directed or undirected. So typically we'll deal with undirected graphs, but a social network, depending on what it captures, could be either an undirected or a directed graph. For example, Facebook is an undirected graph in the sense that if I know you, you know me, right? So whereas Twitter is a directed graph, because if I follow a person, that person need not follow me. So an undirected graph means the edges connecting the nodes are undirected. So again, so you have the vertices are called nodes and edges are the ones that connect the vertices. So if there is no direction for the edges, it means the communication or the interaction or relation is in both directions. So that's what an undirected edge means. Whereas a directed edge means it's like a Twitter. So if you have an edge from the user who is following the other user, so 0 follows 1. So there is an edge, directed edge from 0 to 1. Okay, so unless 1 follows 0, you won't have an edge back. So it's an one direction interaction or communication. Okay. So a graph could be used to model all the complex real world networks. So it could be a network of cities where each node is a city and you have roads connecting the cities, or it could be the plane connections between the two cities, or whatever the way you can connect between the two cities, you can model as a graph. Similarly, network of airports, and the reachability between two airports could be modeled as an edge. Social networks like Facebook, so 0 and 1 know each other, friend for each other. 0 and 2 are friend of each other, so these could be modeled as an edge. Communication networks, you could have each node as a router or a network, and if there's a link between two routers or two networks, then you have an edge, the corresponding graph. So a graph basically captures the kind of the network, the users, the nodes, the networks, the whatever the entities you model as can be modeled as a vertex, and the relation or interaction between the entities can be modeled as an edge. Okay, so now how you store information about a graph. So this is very useful if you really are going to implement a graph, but it's also good to know in general how you store information about a graph. Now we could use two kind of information storing facilities called the adjacency list or adjacency matrix. So an adjacency list is a kind of an array of lists. Okay, so if you're really implementing, it would be an array of linked lists. Okay, so for each node you have an index in this array, and what you store are the neighbors of the node. So neighbors means if we have an edge to a node, that node is called a neighbor. So for 0, 1 and 2 are neighbors. For 1, 0, 2 and 3 are neighbors. For 2, 0, 1 and 4 are neighbors. So we basically store the neighborhood information in the adjacency list. Okay, and you could store the neighbors in any order, but typically you store it in the increasing order of the node IDs. So each user, again in a social network, is given a unique ID. Okay, so that's what we do from a graph theory point of view. Each node or vertex has a unique ID. Now, the number of neighbors for a node is also called the degree of that node or the degree of a vertex. So, degree of a vertex is nothing but the number of neighbors. So, node 1 has 3 neighbors, so its degree is 3. Node 0 has 2 neighbors, so its degree is 2. Node 4 has 4 neighbors, its degree is 4. Node 5 has 3 neighbors, its degree is 3, and so on. So that's what we mean by degree of a vertex or a degree of a node. So we will use this terminology in several places in this course. Now, the adjacency matrix is another way we can store information about a graph. Now, typically it is like a binary matrix, but if you have weights for the edges, sometimes the edges could also have weights representing something about that, some weight or level of importance for that edge, or something that captures the information about the edge. For example, the distance between two cities could be the weight of an edge, or the cost to go from one airport to another airport could be the weight of an edge. But most of the times we'll deal with undirected graphs with no weights for the edges. Sometimes in this course we'll look at weighted graphs also. Okay, so an undirected, unweighted graph looks like this. That is in the matrix. So you have here is a square matrix, and an entry is either a 0 or 1. If there's an edge between two vertices, you have 1. If there's no edge between two vertices, the entry is a 0. So you have an edge between 0 and 1. So in row 0, column 1, you have a 1. You have an edge between 0 and 2, so 0 and 2, row 0, column 2. So you see here, there is no edge between 0 and 3, so the entry is 0. No edge between 0 and 4, so the entry is 0. Now, not only this, you can see the adjacency matrix is kind of like a symmetric matrix, in the sense that for row 0, for node 0, the row is like this, capturing whether node 0 has an edge with 1, 2, 3, 4, 5, 6. Now, the column also captures this information, that whether node 0 has an edge with 1, 2, 3, 4, 5, 6. So the row entries for node 0 are going to be same as the column entries for node 0. Similarly, the row entries for node 1 is going to be the same as the column entries for node 1. So in this sense, the adjacency matrix for undirected graph could be called a symmetric matrix. Okay, and the diagonals, you notice, are always zeros, because unless there is what is called a self loop from a node to itself, you have a 0 for the diagonal. And it's called a symmetric matrix in the sense that if you keep a kind of a mirror, it will be like a reflection. So you have 1, 1, 1, 0, 0, 0 is same as 1, 1, 0, 0, 0, 0. Then 1, 1, 0, 0, 0, 0 is same as 1, 1, 0, 0, 0, and so on. Okay. Now, you could store information about a graph in either of these two ways, adjacency list or adjacency matrix. And when you work with some of the tools that I will be sharing with you, or will be using this later in this course, you would need to know how to store this information. Now, we will not really use this format for the adjacency list, but when it comes to that point of showing the demonstration of the tools, I'll tell you the exact format we'll use. But this is what we are still going to capture, that what are the edges from a node between two nodes. Okay. Now, one difference you could see between adjacency list and adjacency matrix is, in adjacency list we store only the edges that actually exist. So 0 will say that it has an edge to 1 and it has an edge to 2. 0 doesn't have an edge with 3, 4, 5 and 6. We don't store that information. So the rest of the nodes, like if 0 is stated to have an edge 2 with 1 and 2, it means, and the other nodes are not listed here, it means 0 does not have an edge with the other nodes. Similarly, when we say 2 has an edge with 0, 1 and 4, it means 2 does not have edge with 3, 5 and 6. That's what it implicitly means. Whereas in the case of adjacency matrix, we store kind of information more explicitly by including a 1 if there's an edge and a 0 if there's no edge. So an adjacency matrix is a kind of you could feel that it takes more space when it comes to storage. That's why we typically include it as a binary matrix, in the sense that for each entry you just allocate a bit, not an integer. Okay. Now, but however, when it comes to a weighted matrix, as I said, you could have a weighted graph. So if there's a weight for the edges, then instead of 1, you will have the corresponding weight value. And if there's no edge between two vertices, you need to have this 0. So at that point, you have to allocate or design the matrix as a matrix of real numbers, means double, or even if the weights are integers, you have to declare them as an integer matrix, not a binary matrix. Okay, so these are implementation details you need to think about. Alright, now similarly for undirected graph, we can also use, similar to undirected graph, you could also use or have a directed graph and store information about the directed graph. Now, so as I said, in a directed graph, you have an edge from one vertex to another vertex, so that we can call it as, say, this edge from 0 to 1 can be called an outgoing edge for node 0, or an incoming edge for node 1. Okay, so in that sense, we can call 1 as an outgoing neighbor for node 0, and 2 as an incoming neighbor for node 0. Okay, so this is an incoming edge from 2 to 0. So from 0's point of view, node 2 is an incoming neighbor and node 1 is an outgoing neighbor. Now for node 1, it has 3 outgoing neighbors, 2, 3 and 4, and it has 1 incoming neighbor, which is node 0. So in the adjacency list, we can either store the outgoing neighbors, we'll follow one particular thing, either store all the outgoing neighbors for each node or store all the incoming neighbors for each node. So just one of the two, and if you just do this, we will be basically capturing all the edges. So here I show an adjacency list where we store the outgoing neighbors for each node. So for node 0, its outgoing neighbor is node 1. For node 1, its outgoing neighbors are 2, 3 and 4. For node 2, its outgoing neighbor is node 0. For node 3, it has no outgoing neighbors, so you don't have any entry for node 3. For node 4, it has 2, 3 and 6 as outgoing neighbors. For node 5, you have 3 and 6 as outgoing neighbors. For node 6, there's no outgoing neighbor. Now, we can also store the data graph as an adjacency matrix, and so here again you follow a convention, either outgoing or incoming neighbors. So here again we'll follow the convention of storing just the outgoing neighbors. So it means you have an edge from 0 to 1. So in the row 0, column 1, you have an entry 1. There is no edge from 1 to 0, so row 1, column 0, you have 0. You don't have a 1. So there's no edge from 1 to 0, so you have an entry of 0. Similarly, there's an edge from 1 to 2, 1 to 4, 1 to 3. So that means row 1, and for column 2, 3, 4, you have a 1. And you have a 0 elsewhere. Now for node 3, you don't have any outgoing edge to any other node. So for node 3, in the row for node 3, all entries will be zeros because it doesn't have any outgoing edge to any other node. Okay. Now, one thing that I want to bring it here, and later we'll use this also in several modules in the course, is the relation between the degree and the number of edges, especially for undirected graphs. Okay. Now, I said that given a graph, if you want to count the number of edges in the graph, until now you may think that I have to manually count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. So you think you have to manually count if I ask you to count the number of edges. You could do that. But from a kind of network science graph theory point of view, you could use this relationship between the node degrees and the number of edges. So this is a relationship. The sum of the node degrees divided by 2 will give you the number of edges in an undirected graph. So like I put here, these are the degrees for each node. So again, by now you should know what a degree for a node is, just the number of neighbors. So for node 0, it has 2 neighbors, so its degree is 2. Node 1 has 3 neighbors, its degree is 3. Node 2 has 3 neighbors, its degree is 3. Node 4 has 4 neighbors, degree 4, and so on. So if I add all these node degrees and divide that sum by 2, like in this case, I add all these node degrees, which is adding up to 20, and divide that sum by 2, which is 10, and this is the number of edges in this graph. The reason is this: so when I count or add the node degrees, I am considering each edge twice, because when I say 2 plus 3, this edge is considered twice. Once when I say the degree is 2, and once when I consider the degree of 3. So when you add up the node degrees, each edge is basically considered twice. So that is why you divide the sum of the node degrees by 2, and that will get you the number of edges. So given a graph, you need not physically count the number of edges, or manually count the number of edges. You can just add up the node degrees, which is kind of more error free, because if you are manually counting the number of edges, you could also do a mistake, and also sometimes it may not be that easily possible or feasible, because if you are given a large graph, you may not be able to accurately count the number of edges manually. So with this approach of just summing up the node degrees and dividing the sum by 2, you can get the number of edges in a graph, in an undirected graph. Now, one other thing you should also realize or be able to do is, given just this information, that if there is an undirected graph, you are not really given what graph it is. You are just given a statement and no picture about the graph, and you are given a statement like this: consider an undirected graph of 7 vertices and 10 edges. Now, just based on this information, and you don't need a graph really. You just given the information about the graph, that it has 7 vertices and 10 edges, then you can get really the average degree of the vertices in such a graph of 7 vertices and 10 edges. And that's what we're going to do now. How to compute the average degree of the vertices by just knowing the number of vertices and number of edges in that graph. You don't need to be given the actual graph. Alright. Now, you should also know this definition for average. So average of some set of integers is basically a sum of integers in that set divided by the number of integers in that set. Similarly, the average degree, by definition of average, could be computed as the sum of node degrees divided by the number of nodes that you're considering to add up to find the sum. Okay, so sum of node degrees divided by the number of nodes. So similarly here, the sum of node degrees is 20 divided by the number of nodes you have in this graph, which is 7. So 20 divided by 7 is going to be the average degree of the vertices. Now, but in order to do this, find the average degree using this approach, you need to know the node degrees, which means you need to know the actual graph. But let us see how we can get around this. Now, from our relation that we saw earlier, the number of edges is sum of the node degrees divided by 2. And even for doing this, we need to know the actual graph. But let us proceed further with this. So now, from this relation, we can get the sum of node degrees to be 2 times the number of edges. That's what I have here, just by cross multiplication. And from this relation here, the sum of node degrees is average degree times the number of nodes. This is again cross multiplication. So we have sum of node degrees in both the equations. In one equation you have 2 times the number of edges. In another equation you have average degree times the number of nodes. So just put things together, we can get twice the number of edges equals average degree times the number of nodes. And if you, so average degree times the number of nodes based on this equation for sum of node degrees equals 2 times the number of edges based on this equation for the sum of node degrees. And from this relation we can get the average degree to be simply 2 times the number of edges divided by the number of nodes. So this is a relationship between the number of edges, the number of vertices, and the average degree. That means you need not be given the actual graph. You could be just given the number of edges and number of nodes in the graph. You can get the average degree of the vertices in an undirected graph. So I could say a social network has 100 users and 1000 edges. What is the average degree of the vertices or of the users in such an undirected graph? You can just plug in this formula. Now, just for completeness, and also so throughout this course we may encounter different types of graphs or the kind of the layout of the vertices and the graphs. So just as a terminology, you should know these are some of the possible types of graphs you could encounter. So a graph could be called a complete graph if you have an edge between any two vertices in that graph. Now a graph is called a regular graph if all the vertices in the graph have the same degree. So in this case each vertex has degree 2, so we call it as a 2 regular graph. So in general, if each vertex has degree k, then you could call the graph as a k regular graph. Now a graph is called a star graph if you have one vertex called the hub, which is connected to every other vertex, and those are the only edges in the graphs. The edges connect that connect the hub to every other vertex. Okay, so this looks like a star. So in a star graph, the hub has, so the n vertices, the hub has a degree of n minus 1 because it's connected to every other vertex, and the other vertices have a degree of 1. Now you call something as a cycle in a graph if you can start from one vertex, go around the vertices, go around some other vertices through the edges and come back to the starting vertex. So you can start with this vertex, go to this, and then to this vertex, and come back to the starting vertex. So actually, so that's called a cycle. Now in a cycle, you can really start from one vertex and go around and come back to the starting vertex. It doesn't matter which vertex you're starting from. So a graph could have cycles, not necessarily, it could have cycles. Now if a graph does not have a cycle, then it can be also called as a tree. So a tree is also a type of graph in which there are no cycles. Okay. So if a graph has a cycle, you could have one or you will have more than a path between any two vertices that are part of the cycle. So for example, between this vertex on the top and this vertex here, you could either go this way or go this way. So it's an undirected graph also. So there could be more than one path between vertices that are part of a cycle. But there will be actually if they are part of a cycle. Whereas in a tree, there'll be only one path between any two vertices in a tree. So if I want to go from this vertex to this vertex, there's only one path between them. Okay, so that's the characteristic of a tree. In a tree, there's only one path between any two vertices. If we have a cycle, there will be more than one path between two vertices that are part of the cycle. Okay, so with this, we'll stop this video.